Now, there is an event A that's a subset of the possible outcomes of the experiment. There's a subset B of outcomes of the experiment, and A and B are disjoint. There's a subset C, and well, C is a subset of S, and C is a subset of A. All the outcomes which are in C are also outcomes of A. And there's a set D, and some of the outcomes in D are also in A, and some are not. Okay, so let's suppose that we have a picture that looks like this. Okay, so we did the experiment, and I say, okay, what's the probability of A? Let's suppose that you have some way of working out what the probability of A is. You work out the probability of A. Now, I do an experiment. I do this experiment. I don't tell you whether or not A has occurred. But I tell you that B has happened. B has occurred. That is, one of the outcomes in B must have occurred. Okay? Now, how would you estimate, what would be your estimation of the probability of A now? This is A, this is B, they are disjoint. If I tell you at the end of the experiment that one of the outcomes in B has occurred, how would you estimate the probability of A? It would be 0, because none of the outcomes in B are in A, so the event A has not occurred. Right? So that additional information has affected your estimation for the probability of A. Okay, what if I tell you that C has occurred? I don't tell you whether A has occurred or not, but I tell you that C has occurred. One of the outcomes in C has occurred. Now, what would you say that the probability of A is? It's 1. Okay? Now, what if I tell you that D has occurred? Should we modify our estimate of the probability of A? Well, we should, because if D has occurred, then there are some outcomes in D which are not in A, and some which are in A. And so if we're saying what's the probability of A given that D has occurred, we have to talk about this intersection. Okay? So sometimes when you're looking at the probability of we want to distinguish between the probability of an event and the probability of an event given that another event has occurred. And that takes us to the discussion of conditional probability. Okay? So another example, A is the event that you roll a 4. B is the event that you roll an even number. Okay? What's the probability of A? The event that you roll a 4 fair die, the event that you roll a 4, the probability that you roll a 4 is 1 out of 6. Okay? Now, if I ask you, what's the probability of rolling a 4 given that you have rolled an even number? What would you say the probability is? Okay. Well, this is how we'd work it out. Okay. If you've rolled an even number, that means you've rolled a 2, a 4, or a 6, right? All of these are equally likely. So the probability that you've rolled a 4 is one outcome out of 3 equally likely outcomes, so 1 over 3. Okay? So our estimation the probability of rolling a 4 and the probability of rolling a 4 given that you have rolled an even number, these are two different numbers. Okay. All right, let's try this one. You shuffle a standard deck of cards. You pick up the first two cards from the top of the deck. What is the probability that you get the 2 of aces? Oh, sorry. What is the probability that you get 2 aces? Not 2 of aces is not a card. What is the probability that you get 2 aces? Okay. All right, so remember, all 2 card hands are equally likely. We had this discussion last time. All 2 card hands are equally likely. So when you're dealing with, what about these 2 card hands? What's the probability of this kind of 2 card hand? Then you say, how many of those are there that meet your condition divided by the number of 2 card hands? Okay? So how do I take 52 distinct symbols and separate them into 2 piles? One is 2 and one has 50. How many different ways? Ordering within the piles don't matter. 52, choose 2. Okay? That's the number of 2 card hands. Okay. How many 2 card hands are there with 2 aces? Well, there are 4 aces, and you have to choose 2 of them. Right? So there are 4 choose 2, 2 card hands with 2 aces. Is that okay? Okay. Now, when you're dealing with equally likely probabilities, all of these 2 card hands are equally likely. All of the other 2 card hands are equally likely. So we had this, what's the probability of the number of events, the number of outcomes in the event you're interested in divided by the total number of events. Total number of outcomes. Sorry, not events. So what do we have? Right? If A is the event of getting 2 aces, there were 4 choose 2 ways of doing that. There were 52 choose 2 card hands. So you divide those 2 numbers, and that's the probability. Again, we're relying on this idea of equally likely probabilities. I have a 52 card hand. I give you 2 cards face down on the table. Okay? I don't tell you what the cards are exactly, but I tell you that the first card is a king. Now, what's the probability that you've gotten 2 aces? Well, you've gotten 1 king, so at most you have 0 aces or you have 1 ace. So you can't get 2 aces. So the probability of getting 2 aces, given that you've gotten 1 king, is 0. So now, the sorts of probabilities we've been talking about, their notation is this. We call these conditional probabilities. And when we write probability of A with a vertical line B, we read that as the probability of A given B. Right? Which is not the same necessarily as the probability of A. Right? So you're saying, what's the probability that one of the outcomes in A has occurred, given that one of the outcomes in B has occurred? Yes?
Can we summarize the idea by saying that the basic idea is that the condition of an event, let's say given B, changes the cardinality of the event B?
Okay. Does given B, does that change the cardinality of A? No, we consider the cardinality of A to be the same, except now in this case, for example, we were looking, if given D, you say, what's the probability of A? Now you're only looking in the intersection, because you know that D has has occurred. So the formula is coming up, you'll see. This is what would happen. Okay, so, all right. In the example we were discussing, probability of A given B is 0. This is how we define the conditional probability. So you see how the intersection comes in there, right? So the probability of A given B is defined to be the probability that this other event, A intersection B, what's the probability of A intersection B, and then you divide by the probability of B, given that the probability of B is not 0. Okay, you can't divide by 0. So that's how you do the calculations. A is rolling a 2, a 4, or a 6 with a 6-sided die. B is rolling a 4, a 5, or a 6 with a 6-sided die. Calculate the probability of rolling an even number. That's the event A, given that the number rolled is bigger than 3. The probability of A given B, the formula is probability of A intersection B divided by the probability of B. So the probability of A intersection B, well, we take A and we take B. We see that it's got two common elements, 4 and 6. So A intersection B is the event of rolling a 4 or rolling a 6. What's the probability of rolling a 4 or a 6? Well, that's 2 outcomes out of 6 equally likely outcomes. So that's 2 over 6. That's the probability of the intersection. We also need the probability of B to do our calculation. So the probability of B is the probability of rolling a 4 or a 5 or a 6. Well, that's 3 outcomes out of 6 equally likely outcomes. So that's 3 over 6. Okay? So now we want the probability of A intersection B divided by the probability of B. That's the conditional probability of A given B. Now a new terminology of independent events. Okay? So events A and B are independent if the probability of A intersection B is the probability of A times the probability of B. Okay, we'll connect that to conditional probability in a minute. A simple example of two independent events. Yes? Yeah, so if you flip a coin, the probability of getting 2 heads is 1/2 times 1/2. If you flip a coin twice, probability is 1/2 times 1/2, right? Okay, so in the case that you have A and B are independent events, the probability of A intersection B is probability of A times the probability of B. Then what happens in the what happens with conditional probabilities? The probability of A given B when A and B are independent events, well, it's the probability of A intersection B divided by the probability of B. But the probability of A intersection B was probability of A times the probability of B. Now the probabilities of B cancel, and you just get the probability of A. What does that mean? It means that with independent events, the probability of A intersection B is just the probability of A. Right? If we know ahead of time that the events are independent, then we don't have to do any special calculations for probability of A given B. It's just the same as the probability of A. Okay? And if you were to, I'll leave it as an exercise. If A and B are independent, and the probability of A is not equal to 0, then probability of B given A will also be the probability of B, right? And you don't have to worry about doing any extra calculations if you already knew how to work out probability of B. Okay, so Those were independent events. So either probability of A intersection B is equal probability of A times the probability of B, or a consequence of that is the probability of A given B is the same as the probability of A, and the probability of B given A is the probability of B, right? So those are independent events. Dependent events are the opposite. If the event is not if the two events are not independent, we say that they are dependent. Okay? Be a little bit careful. Some people confuse independent versus disjoint, or independent versus mutually exclusive. And these are two different terminologies. They mean two different things. Okay? If I roll a fair die twice, the probability that that the first roll is a 1 and the probability that the second roll is a 1 are independent. Okay? If I say or I could say A is the event that the first roll is a 3, and B is the event that the total roll of the two rolls is a 7. Those will turn out, if you do the calculations, you'll see that they're not independent. Yeah. We roll a fair die. Okay, we roll two fair die. Okay. And we record the results as ordered pairs. This is the result of the first roll. Yes?
Sir, I understand as to how to visualize a mutually exclusive event. So that
Yeah.
would be two separate sets of aside.
Yeah.
But how would we then visualize independent events? Like how do we look at them?
Yeah, I'm not sure I could do that with a Venn diagram.
So how would you suggest thinking about it? Because I do think that there's similarity.
Okay, so the way I think about it is that if A and B are independent, telling me about B does not affect A. Right? So what I could do is I could imagine that every day, okay, right now I'm going to roll a fair die and I'm going to look on the internet and see what the temperature is in the city right now. Okay? Right? So I do this experiment. And then I tell you, okay, this was the temperature in the city. Does that affect your estimation of the outcome of rolling the die? No, it doesn't.
So could we say that it's from different sample spaces?
No, it's all supposed to be within the same sample. A and B are supposed to be subsets of the same sample space. Okay. Yeah?
So would this situation be independent or mutually exclusive?
Yeah. See, okay. Knowing the temperature does not affect my estimation of the outcome of rolling the die. So those two events are independent. Okay? But they're not mutually exclusive. I can imagine a set of ordered pairs. The first element in the ordered pair is the roll of the die, and the second element is the temperature. A is the event that the first die gives a 1. B is the event that the second die gives a 2. Independent or dependent? Okay, we said they're independent. Okay, so how do I show that? Okay, so the probability of A is 1/6, the probability of B is 1/6. There's 36 ordered pairs, right? 6 results for the first one and 6 results for the second, 36 ordered pairs in my sample space. Okay, so the probability of A intersection B is the probability of exactly this outcome, rolling a 1. For the first die gives a 1 and the second die roll is a 2. That's one outcome out of 36. But that's the same as probability of A was 1/6, a particular roll of the first die. and probability of B, one particular roll of the second die, that was also 1/6. So if I multiply them together, I get the same as the probability of the intersection. So in this case, the probability of the intersection of the two events was equal to the multiplying the probabilities of the two events. And so the two events are independent.
It's an identity that whenever the probability of intersection is equal to the simple multiplication of individual probabilities, the events will be independent.
Yes, this is the definition of independence, that if the probability of the intersection is equal to the product of the two individual probabilities, then we say that the two events are independent. Now we come to an idea called a multiplicative rule. As we've seen before, sometimes you want to write some quantities in terms of other quantities because it might be easier to do the calculations for you. Okay? So recall the definition, probability of B given A is the probability of B intersection A, which is the same as the probability of A intersection B, divided by the probability of A. So I can now write, I can bring one term over to the other side. I can write the probability of A intersection B is equal to probability of A times the probability of B given A. Okay? I can also write probability of A intersection B as the probability of B times the probability of A given B. Okay? So sometimes when you're doing your calculations, you might find if you need to calculate probability of A intersection B, you may not be able to do that directly. But one of these two forms, for these equivalent forms for the intersection, probability of the intersection, those might be easier. So you might want to use those instead, right? Okay. We won't use this a lot, but in principle, you could develop formulas for the probability of the intersection of 3 events, the probability of the intersection of 7 events, and so on and so forth. As the formulas get longer. Okay. So this is a multiplicative rule for probability of a triple intersection. Okay. And in principle, we can write a nice long rule for probability of the intersection of n events if we wanted. Okay, we don't want to do tediously long calculations in this course. It's more important to understand the ideas than to be able to do lengthy calculations. Okay. All right, so let's use this multiplicative rule. Okay. I have 3 black socks and 7 white socks in a drawer. You select one and you don't replace it. Okay? Then you select another one and you don't replace it. Now I've got 2 randomly selected socks in my hand. Okay? Okay. Let's say A is the event that the first sock was black, and B is the event that the second sock is white. Let's say I start thinking about it and I say, okay, that's getting a bit difficult for me. And I say, okay, I can always rewrite. I can rewrite using the multiplicative rule. The probability of the intersection can be rewritten. Probability of A given B, one way of writing that is the probability of A times the probability of B given A. Okay? What was A again? Drawing a black sock first, right? What was B? Where? Okay. All right. What's the probability of A? what did we have? 3 black and 7 white. We had 10 socks. 3 out of the 10 were black. So what's the probability of drawing a black sock at random first? 3 out of 10. Okay, so we know how to find probability of A. Okay? What was B? B was probability of drawing a black sock. Sorry, probability, you're right, probability of drawing a white sock, sorry. And on the second draw. B given A means you already took out a black sock. And now what would be the probability of drawing a white sock? Right, so you have 9 left. Out of those, 7 of them are, the original 7 are still there because you drew a black first, so the white ones are still there. So probability of B given A is 7 out of 9. Okay, so I know how to calculate, in this equation, I know how to calculate the elements on the right-hand side. And maybe for some, might be more complicated to calculate the probability of the intersection directly. But these two I found, these other probabilities I found fairly easily. Okay, so once again, you had 3 black socks out of 10 total socks. So the probability of drawing a black was, first was 3 out of 10. B given A means I'm going to draw a white sock, but I've already drawn a black sock first. So I've got 9 socks left, and 7 of them are white. So that probability is 7 out of 9. So now, the probability of the intersection is the product of those two probabilities. So that was 3 out of 10 times 7 out of 9. I think that works out to 7 out of 30. All right, now let's also consider conditional probabilities and complements. Remember we said sometimes probability of A is not so easy to find, perhaps, but the probability of A complement I can find, and then the probability of A is 1 minus the probability of A complement. Okay? So what about maybe that you could also find something helpful for finding the probability of complements when you're talking about conditional probabilities. Okay, so once again, probability of A is the same as the probability of 1 minus the probability of A complement. Sometimes finding the probability of A complement is easier than finding the probability of A. So if I wanted the probability of A in such a case, I would first find probability of A complement, and then I would take 1 minus that probability. Okay? So sometimes that's easier. Okay. So for conditional probabilities, the probability of A given B is equal to 1 minus the probability of A complement given B. Okay? And once again, perhaps probability of A given B is more difficult than finding probability of A complement given B. So you find the probability of A complement B first in such a case, and then you find the probability of A given B as 1 minus the probability of A complement given B. Okay? And directly from the definitions, you should be able to. A person draws 2 cards at random from a standard deck, 52 card deck, fair deck. And there's no replacement. What's the probability of drawing 2 cards of the same suit? There are 4 suits, right? Hearts, clubs, spades, diamonds. Right? So what's the probability of drawing two cards of the same suit given that the first card drawn is the king of hearts? How do you work that out? Let's see if okay. How many two-card hands are there? There are 52, choose 2. Let's just write down a few things that we know, okay? We know right away 52 two-card hands. 52, choose 2 of those. Anything else that we know? Okay. We know that we've drawn the king of hearts. In order to get a two-card hand where both cards are from the same suit, what has to happen? I have to draw a heart card. Okay, how many hearts? Okay, so there, in a standard deck, there are 13 hearts. And we drew the king of hearts. Okay? So, if I have a deck and I've removed the king of hearts from it, then there are 12 heart cards left, and I want to draw one of those to get a second heart. So 12 heart cards out of 51 cards. So what's the probability? 12 out of 51? Okay. So we reasoned our way to getting the answer. 12 out of 51. Okay, so that was an easy one. We didn't have to go to the definitions or anything. Okay. All right. So there are two children in a family. There's a younger child and an older child. Let's assume 50% chance of boys and girls. What's the probability that the younger child is a girl? That's one question. Okay. Second question. What is the probability that the younger child is a girl, given that at least one of the two children is a girl? Okay. Can you think about that for a minute, and then we'll work through it? I'll give you 1 minute to work it out. Okay. What is the probability that any randomly selected child in the universe is a girl? Let's say 50%, yeah? Okay. What's the probability that the younger child is a girl, given that at least one of the two children is a girl? We're assuming 50% chances. Okay, well, this is a small enough problem that we can we can just list all the possible outcomes, right? So let's list the outcomes. Younger child, older child, boy or girl. So we could have boy, 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 girl, girl, boy, and girl, girl. All the outcomes are equally likely. Okay? So the probability that the younger child is a girl is 1/2. 2 out of 4 equally likely outcomes. We already said that. Okay, let's continue with this. A is the event that the second child is a girl. B is the event that at least one of the two children is a girl. Well, that's boy, girl, girl, boy, or girl, girl. Okay, so what we were asked for was A given B. We were asked, what is the probability that the younger child is a girl, given that at least one of the two children is a girl? So in the notation that we've used, we've been asked for the probability of A given B. Okay, so we need the probability of A is what? 2 out of 4. The probability of B is what? 3 out of 4 equally likely outcomes. A intersection is boy, girl, and girl, girl. So what's the probability of the intersection? 2 out of 4. Okay, so the probability of A given B is the probability of A intersection B divided by the probability of B. That's the definition of conditional probability. Right? And we found the probability of A intersection B was 2 out of 4. And the probability of B was 3 out of 4. So we get 2 out of 3. Okay, so let's do a few more of these so that we feel comfortable with this. Let's suppose that 20% of LUMS applicants are accepted. 50% of accepted students get a hostile accommodation. What is the probability of being accepted and getting a hostile accommodation? How would you work that out? All right, so when you, on the test, you want to say something like, let A be the event that, let H be the event that, the probability that I want is A intersection H or A given H, something like that. Okay, so A is the event that the applicant is accepted. H is the event that a successful applicant is given a hostile accommodation. Okay, so what were we given? We were given that the probability that someone is accepted is 0.2, and the probability that hostile accommodation has been given that someone has been accepted is 0.5. What is the probability that we were asked for? We were asked, yeah, see? Probability of being accepted and getting hostile accommodation, that's the probability of the intersection. Okay, so we can use our multiplicative rule. The probability of, because we're given probability of A and we're given the conditional probability, so we can use the multiplicative rule to find the probability of the intersection. So probability of the intersection is the probability of A times the conditional probability. We were given that the probability A was 0.52. We were given that the conditional probability was 0.5, and so we get 0.1. Okay, that's an easy one. Okay, another one. You flip a fair coin 3 times. What's the probability of getting 3 H's? 1/2 times 1/2 times 1/2, right? So if I said the event A is getting an H on the first toss, and the event B is getting an H on the second toss, would we call those two events independent? Yeah. So in some sense, you could say that the coin doesn't remember the result previously, right? Okay. Okay. Okay, let's try this one. You flip a fair coin 3 times. What's the probability of observing exactly 1H in 3 flips? Probability of observing 1T is the probability of observing THH, or observing HTH, or observing HHT. That's 3 results. Okay, so one way of looking at it is that's 3 results out of 8 results, right? 2 to the 3, 8 possible distinct results. So that would be 3. That should be 3 out of H. 3 out of 8. You flip a fair coin 3 times. You're given that there's at least 1H. So now we're doing a conditional probability. If you flip a fair coin 3 times, you observed at least 1H. What's the probability that there were actually 2 H's? Exactly 2 H's. A is the thing we're interested in, the probability of observing 2 H's. And we were given B, that you got at least 1H. Okay? And we're interested in the conditional probability, the probability of A given B. Okay. So the probability of A given B is the probability of A intersection B divided by the probability of B. Okay. Now, I claim that the probability of A intersection B is equal to the probability of A. Why is that? B is a subset, right? No, sorry. A is a subset of B, right? The outcomes of getting at least 2 H's, that is, you got 2 H's or you got 3 H's, those outcomes are contained within the event of getting at least 1 H. If you have at least 2 H's, you're guaranteed that you have at least 1 H. That condition has been fulfilled. So since A is a subset of B, the intersection is just A. Right? So this is what it looks like. Here I have A, and it's a subset of B. Every outcome in A lives inside the set of outcomes that are in B. So if I take the intersection, what are the things that are common to both of these sets? That's just A. Yes?
Are B and A dependent?
Yes. Are B and A dependent? Yes, they will be dependent. Okay. So that's why you have this simplification here. Probability of A intersection B can be simplified as A. Okay, so that's probability of A divided by probability of B. Okay, how many outcomes, what was it? How many outcomes have at least 2 H's? Right? And out of the total number of outcomes, how many outcomes have at least 1 H? Well, 7 out of the 8 outcomes. What was A is the outcome THH, HTH, and HHT. Those are 3 outcomes with at least 2 H's. And the outcome with 3 H's is also has at least 2 H's in it. So there's another outcome, HHH. So those are 4 outcomes out of 8 possible outcomes. Okay. B was at least 1 H, right? So what's the complement of that? No H's, so 3 T's. That's 1 outcome out of the 8. That's the complement. So then the 1 minus that is 7 out of 8. Okay, so we get 4 sevens. More sock problems? You have two blue socks, 3 red socks in a drawer. You take out one sock without replacing it. You take out another sock without replacing it. Okay. So let's say B1 is that the first sock drawn is blue. B2 is that the second sock drawn is blue. Let's say I want the probability of B1 intersection B2. Okay. How might we do that? We had 2 blue and 3 red of 5 total socks. Okay. So one answer is 1 over 5 over 1 over 4? Times 1 over 4, you said? Okay, any other suggestions? Okay, let's reason our way through it. Okay, so B1 is, the first one is blue, B2 is the second one is blue. We want B1 intersection B2. Okay, so we use our multiplicative rule again. Probability of B1 intersection B2 is the probability of B1 times the probability of B2 given B1. Okay. Probability of B1. You had 2 blue socks out of 5 socks, and you picked one of them. What's the probability that it was blue? 2 out of 5. Okay. B2 given B1 means you took out one sock, and it was blue. So there was 1 blue sock left, and 4 total socks left. Right? So the probability of taking out that 1 blue sock out of 4 socks is 1 out of 4. So 2 over 5 times 1 over 4 is the answer. Okay. Any questions about that one? Okay, this is a nice one. Because sometimes people's intuition misleads them on this one. Okay. I've got prisoners. They forgot their names a long time ago. They've been in jail so long. So we just call them by their numbers, 1, 2, 3, 4, 5, 6. One of them is to be released. Okay? One of them is to be released. Okay. So this is how we're going to do it. We have 6 marbles. 5 of them are white. 1 of them is black. Right? This is the same as drawing a short straw, right? Right. So 5 of them are white, 1 is black. Okay? Prisoner number 1 gets to take out 1 marble first without looking in the bag. If he takes out a black, we let him go. If he didn't take out a black, then he gets to stay. He puts his white marble back. So no, he doesn't put it. He doesn't put it back. There's no replacement. Now prisoner number 2 has the chance of being released. If prisoner number 2 draws the black, then prisoner number 2 is released. All the others get to stay. If there's no replacement, if he hasn't been released, if he hasn't drawn a black, there's still a black in the bag, then we go to prisoner number 3, and we keep going like this. Okay? So that's how we're going to select who's going to be released. Okay. Is this fair? Does every prisoner have an equal chance? How many people say that it's fair? Okay. Nobody thinks that this is a fair way of doing this. It looks like it looks like the probability of release is dependent upon some previous thing that's happened. Okay. It's fair? Okay, one person says that it's, 2 people say that it's fair. Okay.
Is this without replacement?
Without replacement. Yeah. Okay, so let's go through this. What's the probability that the first one goes free? 1 black marble out of 6 marbles. 1 out of 6. Okay. What about the second one? Okay. Release of the second one requires that the first one was not released. So there's a 5 out of 6 chance that the first one was not released. Now there are 5 marbles left. 4 are white and 1 is black. Okay. So now the probability of release is 1 by 6. And if we keep going, we keep going, and in fact, everyone has a 1 out of 6 chance of being released. Okay? Well, what's the probability that the second one is released? In order for the second one to be released, the first one had to be not released, which had a probability of 5 over 6. So the first one would have to be not released, and this person would have to draw the black marble. Okay? The probability of drawing the black marble now is 1 out of 5. But then you have to multiply that by the probability of, right? So if you go through this, same thing keeps happening the same way.
How many times is it going to multiply the probability of
Right. So you'd have to multiply, 5, 6 times 5, 6 times. And then the next thing you, yeah. Okay. So for the result for prisoner number 3 is left as an exercise. You should work through that. And you'll see again that it's 1 out of 6.